jump right into this. So we all like slice genus and whatnot. We all like to think of knots in S3, which is the boundary for ball, and ask, look at surfaces in for ball that are properly embedded and such that the boundary of F is mapped onto K. And we like to know, for instance, what is the minimum genus of among all such. And this is a slice genus, and we know pretty much, we know quite a lot about it. We have a lot of good lower bounds. Coming from the signature, more recently from Al and S, or another invariant called nu plus that maybe I'll introduce later. So we have a decent number of lower bounds. But that's not what I'm going to talk about today. And what I never said was, orientable. This is what usually we think about when we say surface, and we might wonder, well, why orientable? So the question is, what happens if we drop this assumption? So the main question is, what can we say about, the minimal genus of slice non-orientable surfaces F minus 4 with given boundary. And you cannot possibly hope. Well, first of all, we need to agree on what minimal genus means. Well, there are two pretty much equivalent definitions, maybe one. So I'll use as a definition for genus, and maybe I'll call it H, is basically B1 of F. And that can, what does it mean? If this is H, and if F has only one boundary component, then F is homeomorphic to H copies of RP2 minus a ball, minus a disk. Right. So you can call the non-orientable genus is the same thing as you can call it the cross-cut number, and you can look at surfaces in B4 and ask, how many RP2s do you need? And for instance, neither of these invariants can give you a lower bound on its own, because for instance, for instance, if you take T 2 to n plus 1, the torus knots, these have signature equal to, I think, minus S equal to minus 2 tau equals to minus 2 nu plus equal to 2n. But the non-orientable for genus, and I'll denote it with gamma 4, okay. Well, in fact, this is the same as the minimal non-orientable 3 genus of these knots. And this is just 1 because they bound the Merkes band. These are there are 2 cables of the unknot, and so they bound the Merkes band, which is just goes around the unknot. Good. So, what do we want to say? Maybe we want to prove something. And we want to prove is joint work. This is not very convenient, is it?
Probably better to write on the bottom board, put the top board up and to write on most of the bottom board to start on the switch.
Right, so what I want to discuss today is joint work with Marco Marengon. And we want to give a lower bound. So we prove that gamma 4 of k is bounded from below by the signature minus a certain invariant that we call phi of k. And the definition of this invariant will come a bit later. But maybe and it's going to be defined in terms of correction terms of surgeries along k. We're going to spend quite some time discussing them later. What you need to know at the moment that's maybe interesting are some properties of phi. So, properties of phi that are phi is a non-negative integer. This could be 0. I don't know. Probably in France you have that 0 is not natural, right? In the UK I never remember, but in Italy 0 is natural. Right, this is a natural number. So in particular it's non-negative. And this tells you that, for instance, if the signature of k is negative, then this inequality doesn't tell you pretty much nothing at all. If the signature is 0, even applying it for the mirror doesn't tell you much, because you're definitely going to get something larger than 0, and that's not very informative. What is cool about this invariant is that it's subadditive. You know, it cannot possibly be a homomorphism since it takes non-positive, non-negative values. So you know, hoping for additivity would be maybe a bit too much. In fact, it's not subadditive. It's not additive, but it's subadditive, which is quite. It's maybe not a too surprising property to find. It's shared with among those invariants also nu plus is subadditive. But what's fun is that if you take a subadditive function, then its opposite is, well, superadditive. So this bound is superadditive. So the bound above is superadditive. Right. And well, we give a definition to sort of the limit of that bound. Right, so since it's subadditive, we can take its limit. This is sort of a well-defined invariant. Oh well, I forgot to say them. This is a concordance invariant. It's a concordance invariant of k. It's itself subadditive. It needs no longer take values in the natural numbers, but this is always going to be non-negative. A priori, it's a real number, although we have no examples whatsoever. And it gives a bound, a corollary of subadditivity and of that inequality, is that it gives a bound on something that we can call the stable for genus. Since, you know, the left-hand side is subadditive, the right-hand side is superadditive, the bound holds for every n, and so this thing is sort of squeezed. And so you have a chain of inequalities where this goes here, this goes there. In fact, this is a corollary of this. Right. Do I want to say something? Well, yeah, maybe I want to give some examples. Yeah. So for So some computations maybe. So for alternating knots and L space knots.
You want some kinetic sun in there?
Yeah, you want that. Right, for L space knots and alternating knots, this is boring. In the sense that it agrees with Orvat and Szabo's Upsilon invariant. Up to a sum. Either that or it's zero. But yeah, let's just pretend that it's the same. And in particular, we can compute it using their methods, or we compute it using our definition, but we can compute it for a fair number of knots. And so, for instance, so what do we want to know? So let's take one concrete example. Let's take T35. The torus knot T35. Then if you trust me, this knot has signature equal to -8, and phi, let's take the opposite. And phi is going to be 3. So the inequality up there is going to tell you that the non-orientable for genus of T minus T35 is at least 1. Okay, this is not particularly interesting. We can actually show that the opposite inequality holds as well by producing an example. And the example can be produced rather easily. So let me get the crossing straight. We are 5, I suppose. Yes. And close it up. And to see an orientable surface, the only thing that we need to do is attach bands. And we don't need to worry about attaching oriented bands. So one thing that we can do is just attach a band here. See what happens. And then we just suck everything all the way down, and we get a sort of one braid. Maybe the way what happens is something like, so you sort of cut here and you start sucking, suck. This thing goes sort of up here, then we can slide, and then it goes here, and then we suck it again, and it goes here. And now this thing is pretty clear at the end. So what it means is that we have attached the band, and we get an isotopy to a slice knot, and this thing happens in S3 across the interval, and we just cap it off from the bottom and obtain punctured RP2 or Möbius band in B4. I'm not entirely sure that this is a Möbius band in R3 or in S3, because when we sort of do the untwisting, I think we actually do sort of twist around the canonical disk that we get here, and so we should get some ribbon singularities somewhere. So I don't think this is the three-dimensional cross-cut, which, for the record, has been computed for torus knots by I don't remember who, but there are some computations using normal surface singularities. It's something that you can compute, at least for torus knots, for some other cases. But yeah, let's get back to.
If it's a boundary of a Möbius band in R3, doesn't that mean it's a cable, two cable of a knot? So therefore it can't be T3.
Yeah, that's good. It's a good way of showing that. Right. So it's a two cable. Right. Maybe another example for another computation. And it's somewhat artificial, but that's what we could do. So computing phi is in general hard, except for those classes of knots. What we could do was compute it, what we can do is compute it for differences of L-space knots. And I think in principle, also for connected sums of L-space knots with alternating signs. But that's sort of, it's not written down properly anywhere. So. Whatever, in a certain specific case, we could compute omega for this difference of L-space knots, and it turns out that it's not so boring. It's a rational non-integer number. It's a sort of painful computation if you do it by hand, but I mean, it can be done. Right. So a little bit of history maybe, just not to make it look like it came out of the blue. So the theorem up there was inspired by work of Batson. In his PhD thesis, he did something. Well, he had a similar statement. So Batson proved that gamma 4 of k is at least sigma k over 2 minus d-invariant, the correction term of minus 1 surgery along k. Right side. I have to think about it for a second. So for the trifold, this thing should be 0. For the negative trifold, this thing should be 0. So it's a 1, and this is a minus. And I'm going to talk about his proof a bit later. It's a bit different from ours, but we'll see about it later. And then more recently, Oswald and Sabo proved a similar inequality using their invariant epsilon. They proved that gamma 4 of k is at least sigma of k over 2 minus epsilon of k. So these three inequalities are all similar. Two of them, our inequality and Batson's inequality, go through the same kind of proof. This is a different proof as far as I know, and it's also different. I mean, formally they were the same, but the right-hand side here is a homomorphism. So actually one can change sign and get the absolute value, whereas this is again something always non-positive, minus something is always non-positive, and it's subadditive, although Batson didn't know it, or didn't prove it at least. And the proof in this case is completely different. It goes step by step. So what they do is they look at an orientable surface, sort of put it in a standard position so that you have a sliced disk, some two handles that are realized by attaching ribbon bands or whatever, and then a concordance, and then they prove that for each of the steps you get a telescopic thing where you get the difference between the two quantities here for the knot and so you get a controlled change of this quantity by each band. Right. And oh yeah, maybe I should mention that since our invariant phi is sort of boring for L-space knots and alternating knots, then our inequality agrees with the best of their inequalities. These are two inequalities altogether, basically. If you compare both of them with both of our inequalities, you get the same thing for alternating L-space and probably connected sums thereof with the right sign by subadditivity. Something that I would really like to know, can our inequality ever beat this inequality? This is something I have no idea of how to prove. I really don't know. If you have any example where you know that this happens, I would be really, really happy to see that. We know that we often beat this inequality. In fact, our inequality is a generalization of this inequality. We don't know the relationship with this one.
The one.
We don't know. If we knew that, we would have an example where this beats. Because you just take the value where you are better, and you get then you get some larger n. But we don't know. No, we don't know. I think that I can prove that for differences of S-space knots. You know, an alternating sum of torus knots, of S-space knots, then our inequality is at least worse than theirs. At best worse. Their inequality is better. Yeah.
But there are
but-
examples where the inequalities are different? Like,
Yes.
right.
Yes. Well, for instance, if you take this one,
Oh, yeah, yeah.
if you take this particular knot, then our inequality is going to be worse. In general, I know of many examples where it's worse. I don't know about examples where the stable inequality is worse than theirs, in the sense that if you take, the inequality is going to be worse if this is integer. If this is not integer, but if you take the sort of the upper, the floor, the ceiling of that number, then you get the same inequality quite often. And I think that this is one of the instances where you do get the same inequality, but I don't know about the general case. Right. Any questions?
Yeah, so what do you get for the sum there, 2 and T23, T5 minus 6? What do you get for
Oh, the
lower
inequality.
bound for the stable gamma 4? Is it just 1?
The lower bound, so signature there is -2 plus 8, plus 16. So the inequality should give you 7 minus 22 over 3, which is probably 0, which is not a good sign.
What's omega? Can you move the board down?
Yeah, sure. And this is the inequality. The inequality on the, okay, this is omega, and this is sigma over 2.
Yeah.
And so this is -1/3.
Okay, so it gives you 1. No, sorry. Okay, it gives you -1/3, yeah. Not 1.
Which is rather uninteresting. I think we had some examples where it did something different, but I can't remember. I don't have the data. I can look them up. And in principle, if you're willing to believe some reasonable assumption on connected sums of space knots, then we can. I can tell the computer to compute it. You can easily compare it with that, with their invariant. Right. So maybe let's try and introduce this invariant phi that I just erased. Give you some idea of what's going on. So correction terms. So the same thing that you said about the other room works here, but you can read the shape. So what happens is that correction term is something that associates an irrational number called d over t to each spin C3 manifold. So this is closed, oriented, connected. And T is a spin C structure. Y. And this is a natural number that's defined roughly in the following way. So you look at the Heegaard-Floer homology in the plus version of the IT, and yeah, those are going to be connected, and let's have the assumption rational homology sphere thrown in, although we'll need to drop it eventually. So this is it's something of a mess in general, but it has a structure of something like a tower plus some finally generated stuff. And the tower is something that goes up indefinitely, and the arrows here denote the action by multiplication by u. This is an FU module where I work over the coefficient for simplicity. And you have this tower, and then eventually, you have some stuff that's one-dimensional in each even or whatever degree up here, and then it's pushed down, and it dies eventually. And this object turns out to be graded, in fact Q-graded, and the degree of this bottom element is called the correction term. As we were discussing over lunch, this is something sort of awfully hard to compute in general, but you can do something for, I don't know, when y is the branch level cover of an alternating link, for instance, and you can do something when y is a surgery along an oscillatory.
Because this is slightly informal, do I ask an informal question? Can you just remind me why this is Q-graded and not like integer graded?
Because cobordism maps in Cyberwitten or in Heegaard-Floer or whatever have rational degrees.
Okay, so I'm grading this by, I take a cobordism to the previous sphere.
You take a cobordism, yeah, let's say morally speaking, you're taking a cobordism to the sphere. And you're looking at the cobordism map, and you want the cobordism. The cobordism map has this weird grading with the square of the Chern class. And the square of the Chern class, when the boundary is a rational homology sphere and not an integer homology sphere, is not going to be an integer.
All right. Okay.
Good. How can we hope to extract multivariance out of this? Well, Jake tells us how to do it. But maybe let me give some properties first. Yeah. Okay. So what's the key property? That these d-invariants satisfy. So if y t is the boundary of a spin C for manifold, compact, oriented, negative semi-definite, so W, let's say negative definite, since we're in the case where the boundary is a rational homology sphere, then there's an inequality telling you that B2 W plus the square of the first Chern class of S is less than 4 times the correction term. A little bit of comment maybe is needed. I think this inequality can be made a bit stronger by putting in the B1 and B3 of W in here, but let's not think about this for a moment. The most discomforting thing is the square of the Chern class, since this is something in H upper 2 and this has no H upper 4. And so when you want to take the square, you have some troubles. But what helps you is the fact that the boundary is a rational homology sphere, or more generally that the first Chern class of the restriction on the boundary is a torsion class. And then you can make sense of this square after taking a sufficiently large multiple or a good multiple in some sense. So this thing can be computable. And this is where sort of the non-integrality of correction terms come from. I mean, this is more really the degree, without more, this is the degree of the map, of the cobordism map associated to W when you remove a ball. And this is actually -0, that is the correction term. Non-integrality comes from. Good. This is the key property that we're going to use, but we want to sort of compute it and associate to this some not invariant. And this not invariant was defined by Jake in his PhD thesis, and then studied a bit more by Nie and Wolf. And I'm afraid that I will adopt their notation. It's definitely more common nowadays. So if you have a knot K in S3, you can look at the sequence of positive surgeries along K, and you can look at correction terms of their spin C structures. So it turns out that spin C of S3 and of K has a good labeling by Z over NZ. So this is an affine space over H lower 1 of Y, right, my Y. And this is Z over NZ for surgery. So you can label it in a sort of meaningful way. And so you can look at D, S3, and K in a certain spin C structure Ti, and you can look at what this thing does. Now you sort of want to normalize this. And so you normalize it by looking at the end surgery along Gianno, the sort of same, the spin C structure with the same labeling. And this thing turns out to be an even integer. And this is independent of n, as long as n is at least 2y. So it's an invariant of k and I. And since it's twice an integer, you don't want to be redundant, you want to divide it by 2. And then you want to take its negative sign, and then this turns out to be a non-negative integer. And this quantity I'm going to call Vi of k. For the reference, Jake used to call it H, and I think the name came from the Freushoff H, right?
Yes.
Right. What do we know about these VIs? Turns out we know quite a lot. Well, in some cases we know quite a lot. So the way I like to think about them, they are sort of slowly decreasing staircase. If you look at I in the values of Vi, then you get a sort of staircase that goes down and eventually touches 0. So you get V0, which is negative, then V1, V2, it's always non-decreasing, and each step is at most of height 1. I'm not going to write this down, but I don't know if you proved it, but definitely me and Wu wrote it down. Did you have it in your thesis?
I think I do prove that.
And for instance, the place where it stops, this has been called nu plus of k, that had appeared on the blackboard earlier on, and this gives a lower bound for the slice genus. This is definitely something that you proved, but not in this form. You didn't define nu plus. You proved this. Good. no, okay, no, sorry. There's a reason, because everything that he did has been done again, at least by two sets of people, well, by two people, three people in two sets. Ni and Wu reproved all these properties, and Peters reproved them wrong. So, it's a bit strange in the literature you find these incongruencies. Anyway, right. So these VIs are nice invariants, and now we can define at last phi of k. This is defined as the minimum over all non-negative m's of m plus Vn of k, almost, of the mirror of k. This is it's just for technical reasons. It's not particularly important. We'll let it here. So graphically, this is easy to see. You look at the staircase, and let's make it a bit more meaningful. And you look at the line of slope minus 1/2, at the set of lines, well, the line of slope minus 1/2 that is tangent to the graph of these VIs. And this tells you that's the phi. So the intercept with the x-axis is phi of k. So in particular, you see that yeah, it's always smaller than nu plus of k, but that's okay. And maybe let me. All right. So, in some sense, this is the Lejeune transform of the VI evaluated at 1/2 or 1, depending on your convention. This is something that Matt Hadden and Maciej studied, and they proved that if K is an L-space knot, then this Lejeune transform actually agrees with Upsilon. And so this is why for L-space knots are invariant agrees with Upsilon. You can look at this function sort of more generally and see what it does. Right, so maybe let's prove something. So recall that we had a proposition that said that phi was subadditive. And
Sorry, what did you say? I'm just this is a Jean transform agrees with epsilon
for L-space knots. Yeah, in this form for the negative class. So yeah, so phi is subadditive. How do we go about proving it? Well, I don't think I gave you any other inequality other than the ones in the theorem than the key property of correction terms. And so we're going to use that. We're going to prove something that's slightly different. We're going to prove that Vm of k plus Vn of L, where k and L are two knots, is always at least as large as Vm plus n at the connected sum. If we prove this, well, we sort of, when you minimize Vm of the connected sum, you can split it into 2 bits, and you're gonna be less than the minimum of these two quantities staying the same. And this is just simple arithmetic. How do we prove this? So this is something that this is a trick that I learned from Owens and Strellet in one of their papers. We're going to build a Floer manifold which is negatively definite, that has sort of some surgery on K, some surgery on L, and some surgery on the connected sum as its boundary. This Floer manifold is this, where 2m and 2n as sort of lower boundary components, and then I attach a zero frame to m here, where m and n are positive. I'm gonna not talk about the case when m and n are negative, or when m or n is 0, but you can do it in that case as well. Some tweaking of the argument. And right, so why is it negative definite? Well, you sort of, if you glue in the two handles from the bottom, you get something positive definite, and you get an essential class of square 0, so this thing cannot be positive definite. It has signature which is at least, it has at least b2 plus equal 2, and b2 minus is forced to be either 0 or 1, depending on whether the boundary is a rational homology sphere or not. But let's see what the other boundary component is. We just do a slide here, and if we do a slide, we get k and twists, and this, where k stays with framing to m, and L now gets framing 2n plus 2n. And this is framing 0. And then we do a dot zero surgery. This thing is actually unknotted from this one, and we can cancel the two handles. And so we get a surgery along the connected sum of k and L with framing 2n plus 2n. So this is an integral homology sphere. And so b2 minus needs to be 1. So this picture here is a negative definite pointer from the connected sum to 2n plus 2n surgery. And well, this is actually part of an even manifold. And so if you want to look at spin-C structure, you have a sort of easy spin-C structure you want to look at, which is the spin-C structure whose Chern class is the 0 class. And in that inequality, having the 0 class is particularly helpful. And so you get an inequality of the form 1 plus 0 is less than correction terms of the various boundary components. And if you, I didn't tell you what the indexing of the spin-C structure was, but the spin-C structure indexed by m corresponds to the Chern class 0. So in this subhandle, the Chern class with framing indexed by n correspond to the 0 class here, and this sort of these glue together with the spin-C structure that has 0 Chern class on the rest. And on the top, the spin-C structure to obtain is the one indexed exactly by this. And when you sum the correction coming from the lens space surgery, roughly, from the lens space, you get exactly that, the minus ones cancel out. It's probably pointless to write down the computation. Right, so maybe let's talk about the proof of the theorem. Okay. So the first step, sort of very classical. It's an inequality that Cameron proved with Litherland back in 78. So, the first step is to relate the signature, the non-orientable for genus, and the Euler number of F. So what is the Euler number of F? Look at the Euler number of F. So recall we have F, which is non-orientable in B4, we don't know, we can't compute its self-intersection because it's non-orientable, but we can still look at the framing induced by F on the boundary. So the normal bundle of F, makes the section, and we can sort of push the surface along that section and look at the intersection that it gets with the boundary S3. So you have your surface here, your node, your surface with possibly some cross caps, and then you have a section of the normal boundary defined everywhere, and you sort of push the knot of itself using this frame. So get a push off of K, and you can measure the linking number of K prime and K. So the Euler number is the linking number between K and this push off. And Golla and proved the quantity sigma of K minus 1/2 of the Euler number of F, right, gives a lower bound for the first Betti number of F. Maybe that's plus sign. And how do they prove this? Well, this quantity is the signature of the double cover of B4 branched over F. And well, basically this is by the equivariant signature. This is the G signature theorem. And then this quantity, so this is the signature of the double cover F, and this is less than B2 of the double cover F, but this is the same as the B1 of the surface F. And now we have one new character in the picture, and we want to give bounds on that. So up to this point, our proof and Batson's proof are the same. What Batson does is, well, he replaces F with an orientable surface that has roughly the same genus, well, roughly the same B1, and roughly the same Euler number, but it lives no longer in the 4-ball, but it lives in a punctured S2 cross S2. And then he said, oh, well, now I have the Euler number of an orientable surface. Well, this is the self-intersection. I have an orientable surface, so I can sort of cap off my knot and use a junction in this format. So roughly speaking, this is what he does, and he does it by attaching a 2-handle with framing -1 along the knot K, and that's where the d-invariant of the -1 surgery pops up. What we do is slightly different and can be thought of as using the adjunction inequality for non-orientable surfaces. Right, so what do? We take, let me redraw maybe the picture in a slightly different way. So we have our non-orientable surface here. Oh, and one small caveat, the proof that Batson gives assumes that B1 of F is odd. So that inequality doesn't see the difference between having non-orientable genus, say, 1 or 2 or 3. It can only tell you that it's at least 3. Oh, yeah. Whatever, you get what I mean. Right, so what do? Is we completely ignore the issue of non-orientability. We add to handle with framing minus n, where n is an arbitrary integer, and we carve off the neighborhood of n. And so we get a cobordism from the boundary of the neighborhood f to this minus n surgery along k. And the weird thing when you have non-orientable surfaces is that it looks like you're carving off the only generator of H2 of this four manifold, but you're actually not. So H2 survives. So this manifold W has B2 minus equal to 1. So if this surface was orientable, then we could remove it, and this would be a null cobordism in the sense that there will be no surface of non-zero square in the complement of the surface. But when it's not orientable, it's a bit of a mess. And the strategy of the proof is now sort of clear. So you look at all possible spin-C structures on W, and you look at how they restrict on the boundary component coming from the surface and the boundary component coming from the top. And now, well, I sort of assumed earlier when I introduced correction terms that everything was a rational homology sphere, and yeah, that's sort of the annoying part. One of the annoying parts of the argument is that you need to make sure that you can define a correction term for this bottom boundary component, which is not in general going to be a rational homology sphere. And in order to do so, you need to talk about bottommost correction terms and some other technicality or twisted coefficients correction terms, and these are sort of kind of annoying. And then you have, if you want to apply a junction, you need to compute the correction term down here. So annoying things, the long list of annoying things that you need to do. You need to compute correction terms for the lower boundary. Let me call it Q, and you need to understand spin-C structures on W and their restrictions. Q and the upper thing that I'm going to call Y. And well, luckily, somebody else took care of this bit. This was done by Levin, Ruberman, and Spelin. And this is mostly bookkeeping with unwrite topology. There's not much content in that part, but it's something like tricky. And I think that's what's odd, or at least what I found odd about this, is that when you have, so for simplicity, we mostly look at the case where n was an odd integer, and in that case, something strange happens, in the sense that, so spin-C structure on the surgery handle body are indexed by age after 2 of the handle body, which is Z. And so you have spin-C structures here. And the strange thing is that, okay, maybe not so strange, when you restrict them to the complement of the surface, you don't get all spin-C structures. And actually those ones are the ones that are not going to give you anything interesting in terms of the inequality. So if you try and use the sort of obvious species structures that are looking at you, you don't get anything interesting, because correction terms associated to the restriction of those species structures to the boundary are sort of unfit to give you any inequality like the one that we need. So you need to look a bit deeper and look at the species structures that are not restrictions of species structures on the surgery handled body. And in some sense, what's weird to me is that you can take half of a restriction. So if you have a species structure on the surgery handled body you restrict it, you can sort of divide it by 2. It's in some sense no longer primitive in H1. And I found it extremely disturbing when we played around with it. And yeah, maybe I'm not gonna impose on you the computation of the square of the term class and all the other amenities that we went through. And I think
So if I have like the m in torus knot and I fix n and I let n go to infinity, how does phi behave?
it's fine in the number of full twists that you add. You're adding full twists, or
Sure, we could have full twists.
yeah, if you add full twists, it's linear.
And what's the constant?
That's epsilon of t and n plus 1, or n plus 1. So
Yeah, I don't know what it is.
yeah, so if you have t m n plus kn, then well, phi epsilon, that's all the same, and epsilon of this is epsilon of t m n plus k epsilon of t m.
But okay, but what's the number epsilon of t m plus 1? Where is that?
They Oshwat and Sabo computed. I should know this. It's basically the signature up to, so for when m is even, this is the signature, and when m is odd, it's sort of the signature minus m over 2, something like that.
So I mean both phi and the signature are linear in adding full twists. Is that?
Yes.
And the
No,
but
the signature, I'm not sure. Right, right.
Lucas just sent me a paper. I thought that.
Okay, but okay, for this knot, okay, linear.
Well, at least up to a bounded error. But if you add full twist, it should actually be linear.
Maybe I thought that's what the. This was a paper of Cameron's actually.
Yeah.
Okay, well, there you go.
But
Right.
maybe it was.
I mean,
it
I
was
was
two
just
full twists or something like that. But,
right?
yeah, but I
So,
mean,
but it should be.
there was that recursion.
Oh yeah,
formula.
two full
Right.
twists. Yeah, two full twists. You're right.
Oh, is epsilon also linear in two full twists, or
It's in one full twist.
it's in one full twist?
In fact, I mean, you can. This follows because you can compute epsilon in terms of the multiplicity sequence of the torus knot. So you basically look at the Euclidean algorithm for m and n, and you get that each of the building. I mean, this is the division of. This is the this is the
When you
division of.
divide in
Yeah.
m into n plus k.
Yeah. And this gives you the building blocks. As far as I know, this was proven by Bodnar and Nemeti.
So, I mean, so the point is if the signature function is linear and phi is linear and the factor is different, then
Yeah, I just wanted to know sort of what the different how the factors compare.
so I mean if very different, then you get that,
Yeah, you do get examples like that. For T35, the note that I was doing earlier. Even without doing any computation, I think that you should prove that the constants are different. So what did I tell you? I told you that right, so signature of T35 was -8 and phi T35 was 1 and gamma 4 of T35 is 1. And so if you take connected sums, but this is not torus, not any longer. Right, I slightly take it back, but I think that the same holds for T34. And if it's not for T34, it's for T45. But one of these two knots should
maybe
be
the
okay.
signature,
Simply,
it's not
yeah,
one
it's
thing.
not eight anymore.
No, it's not 8, but you know, the same argument sort of works, where you have the inequality that we gave, the one that Oshpet-Szabolcs give is sharp. Is sharp in the sense that gamma 4 is exactly sigma over 2 minus upsilon. And then if you take connected sums,
Yeah, but
Oh,
if you
hold on.
freehand,
right, the signature is not additive in that sense. Sorry. No, yeah. So the thing that you were saying is that signature of T34 plus 6K is linearly paired, right?
Yes.
Right. You want to know the constant, and that I don't. Right. Okay. Do you know the constant?
yeah, I mean, the signatures asymptotically, it's 4/3 of the genus, or in this. So,
Can I not embarrass myself and do that?
yeah, maybe we can do it. I mean,
Right,
the
maybe-
interesting
maybe
question
Yeah,
we
is,
have a cookie that,
I mean, the interesting question is it's different from pi, right? So do you get a linearly increasing bound for gamma 4?
We do get a linear increase.
Yeah, I mean, that's all we.
Right.
Also, doesn't this one always bound to Mobius bound T3? You mean like
Yeah.
but maybe,
Oh.
T4?
Yeah.
but maybe for T4,
Oh, isn't the same.
I think the T45 bounds Mobius, but it's not apparent, but I think it does. Yeah, by the same trick, draws in here. You get Mobius.
I think you get a trefoil. I think you get a trefoil in the symmetry. Anyway.
So how about we turn to the common area upstairs and, I should bring out the cookies and feed you all the cookies since I promised, or multiple cookies.
That's what you're looking at, right?
That's right, okay. And let's thank Marco.